We ready to start? Okay, good morning, folks, and welcome to our EM-X for March 2026. And we have two distinguished speakers, both with a European theme, working in Europe these days. And so we're looking forward to these talks today. Seems worthwhile at this point in time, reflecting on the importance of international collaborations and multicultural understanding, which we electron microscopists and researchers I think, demonstrate how important this is, and we're pretty good at it. But with that in mind, I'd like to remind everyone that the abstracts are due at the end of this week, March 6th, for the 21st International Microscopy Congress, which will be held for the first time in the United Kingdom, and in fact in Liverpool, which is the town where I was born. And contrary to common belief from those people who go back a ways, we didn't always live in a submarine, yellow or not. And if you're a real Scouser, like I am, you're either red or you're either blue. And I think people know which one I am. So without further ado, I'll introduce Hua Chu, who will introduce our first speaker, the bio speaker. And afterwards, Colin kindly agreed to introduce Christoph in the second half. So Hua, it's all yours, please.
Okay, good morning, everyone. It's my great pleasure this morning to introduce you Professor Xiaodong Zou from the Department of Chemistry, Arrhenius Laboratory at Stockholm University. Xiaodong is very well known for her pioneering work in electron scattering and also electron diffraction for biological and beam-sensitive materials. And her work has been immensely impactful in the field of electron diffraction and electron scattering. And she is a member of the Swedish Royal Society and many other awards as well. So this morning, she's going to tell us her work on serial electron diffraction beyond micro-ED for high-resolution low damage protein ligand interactions. Xiaodong, welcome.
Thank you very much, Hua Chu and Robert, for the invitation. And it's my great pleasure to show my work here. So I will first take it that I'm really not a structural biologist. I'm mostly working on structural chemistry, crystallographer. So we have been developing electron crystallography methods for structure analysis. So at the early 90s, we have been mainly focused on imaging because you know that if you have images, you can get the phase information directly from the image and use it for structure determination. So, we developed different programs for doing that and combining it with electron diffraction for studying beam-sensitive materials. And since 2008, we have been moving to electron diffraction, mostly 3D electron diffraction, or it's also called the micro-ED. And the reason for that is that actually it's much easier for you get higher resolution data for beam-sensitive materials. And since 2015, we find out actually it's even necessary to develop further. We call it serial electron diffraction, and because when we have even more beam-sensitive materials, and really it's not enough to collect 3D electron diffraction data. That is what I want to share with you today. 3D electron diffraction or micro-ED, so that has been developed first by the Koch group in Germany. They call it ADT. And they use precession mostly to in combination with the goniometer tilt. And we call it rotation electron diffraction because we are using bin tilt in combination with goniometer tilt. And Tamigona call this method micro-ED. They are mainly using stage tilt and with continuous rotation. So now I think everybody is familiar with this method. So just to show you a schedule here. So now when you collect the data, you find the crystal, you tilt the grid, and then you collect a series of data. And then you combine this data with known angles and to get three-dimensional electron diffraction data. From there, you can get the HKL file or MTZ file, and then the rest of the process is similar to X-ray diffraction, so where you can directly get the structure in the same way as what you do with protein crystallography using X-rays. And through the years, we built up a platform for automated data collection, data processing, and it's called Instamatic. And there we can do continuous rotation electron diffraction, including crystal screening, find suitable crystal, data collection, and so on. And so this method has been used, developed in very just material science microscopes in the cryo-EM, and there is a similar package called the EPUD that you can use for data collection. Actually, my group has been mainly focusing on inorganic materials like zeolite, metal-organic frameworks, what is covalent organic frameworks, pharmaceuticals. And just since 2015, when I heard about the work of Tamigona and on micro-ED, I get excited to work with using proteins. So then we started to study this using micro-ED for study protein structures. We find a lot of challenges. The first thing is that it is interesting using electron diffraction because you can really see hydrogen positions more easily, and we really want to use it for study protein ligand interactions and also to look at the charge state in proteins because electrons are charged. And when we started, we find a lot of challenges. First, it's a sample preparation. And nobody really is familiar with knowing how to grow small crystals. So the crystals we usually got was too large, and the radiation damage is also a problem. And so data collection, when we collect the data, we mainly get very low resolution. For example, let's see how typically about 2.53 angstrom resolution. So you really cannot see very much details when specifically if you want to see the protein ligand interactions, for example, you see here. And so that is one of the reasons we developed serial electron diffraction. And using serial electron diffraction is that you only collect one frame, diffraction pattern per frame. So that is, so that you have the crystals here, and you take the image, and that's what you see here. You use the segmentation to find where the crystals are, and you go to different places to collect the data by stepwise. First mapping the crystals, and you go there to collect the data. And in this way, we can get much higher resolution data. Let's see how we can get 3,500 crystals per hour. the data collection. And so, and this method is really developed for on the microscopes related to material science. So when we go to the life science microscope, and so we developed we call it continuous serial electron diffraction. So we changed it from, instead of stepwise data collection, so we just move the grids continuously and collect the data like a movie. And so in this way, the data collection is really depends on the speed of the camera and also how fast the grids can be moved. And using this, we now can collect like 3,500 crystals per minute. So you get a lot of data. And so this is really easy to implement because you don't need a tilt, you don't need anything. It's just a camera and you move the grid. So it's much easier. And of course, we will collect a lot of data where there is no crystal, and so that we have developed online data processing so that we can remove those crystals frames that don't have anything. With this one, of course, you need to really have, I will show this slide a little bit later. And you need to get a lot of crystal. And so in order to do this, we have to developed a method called the RAMIC, rapid crystallization, and to get microcrystals, a lot of microcrystals. How to do this? So that we start either just normal crystallization and when we get some crystals, we use vortex to grind the crystal, make it smaller. So this is how it looks like. And then we wait a few minutes, a few seconds, and then we make this in situ fragmentation and regrowth, and then we will make another vortex, and so on several times. So the crystals will become smaller and smaller, and we get a lot of crystals. So this is the approach we use to get microcrystals or sub-micro-sized crystals, and without using the FIB, which is normally another method to use. So the crystal you see here, it's like milky, very. This is typical crystal slurry we want, and we also developed our software code to connect this one, integrates this with QuizFair, which is used for data processing of serial crystallography data using collected by XFAIR or synchrotron. And we used Cosetta to do the data pre-processing and then in combination with QuizFair to do the data processing. So typically, that is what you see here. You find on the grid a lot of crystals, and so you just move the stage, and then you will get all the crystals from one by one. And so this is a lysosome data. So we use a triclinic lysosome to check about the completeness, because you know that if you don't tilt and you will get if there's preferred orientation, there will be a problem. But if you have a preferred orientation, what you can do that you can tilt your crystal grids 45 degrees, and then you can collect the data at that angle. So with this, we can collect the data to sub-angstrom resolution. From there, you can see very well the water molecules are clearly resolved, and also you will see a lot of hydrogen positions very, very clearly. So this this is another protein, proteinase K, and so this is a bigger crystal. You use the ceramic to grow nanocrystals. So these are the nanocrystals. You see the grids. So you select the different types of grids, grid squares, and you collect the data. So we collected data from 0 degree and 45 degrees to get the completeness, and the 4 grid squares and all the data. So we could get 30,000 frames indexed. So this is the structure you can see here. And the green one is the 0 electron diffraction structure. It's 0.95 angstrom, and the X-ray structures is 1.27 angstrom. So we can really get the structure better than X-ray, and all the hydrogen positions can be easily found, and the water molecules. For protein ligand interactions, actually small crystals have very good advantage, because you can allow the rapid and uniform soaking of the ligand. And so what we are showing here is that when we first load the crystal on the grid, and then we back plot just manually the liquid, and then we apply ligand. It's about 10 micrometer, and then we make a back plot again, then plunge freeze. So this is very simple. You don't need anything else, just manual plotting. And so on grid soaking, so this is 1.5, so it's 2 micrometer. And so this is how we get the ligand in 3 seconds into the proteins. So this is a protein. It's called a DTPAA with a heme group. And so we can see the water molecules here is 1.3 angstrom resolution, 21,000 frames merged. And so this is after the ligand soaking. In 3 seconds, you can see that the water molecules has been replaced by the acid molecule. And this is another protein. It's called urate oxidate. It's 1.25 angstrom, 56,000 frames. And so you can see this ligand by on-grid ligand exchange. So exchange to this ligand in 3 seconds. And so this is the resolution we got. So we only used 38,000 frames to get this one. So very fast ligand exchange, and we can get really good data and very high resolution. In order to make this method high throughput, so we developed it's called on-grid real-time ligand screening by micro-ED, combining micro-ED and the zero-ED. So how do we do? So as we said, we use this protein. It's human MUTT homolog 1. So this cancer target, and so we can introduce different ligand in different grids, and so that we can look at the structure of each grid using micro-ED. Micro-ED is much faster data collection and data processing, I will tell you. So this ligand screening takes only 15 minutes. So that includes data collection and the data process to get the ligand, get the structure. And so different ligands, you see that about 30 minutes to 50 minutes, and you can get the structure. And when you know there is a ligand in here, and then you can go ahead to collect 0 electron diffraction data and get much higher resolution data. So this is a workflow you can find, and basically for data collection it takes about a day to data processing, data collection, and to get the structure in total. And you can also say that if there is no ligand, and then we don't need to go ahead to collect theory electron diffraction data. So this is a workflow that will be very, very useful to do. And in order to know if the ligand is incorporated in the protein, and we developed a software. It's called Autolay. It is automated real-time and data processing. So it's both. You can use both real-time or batch offline data processing. It's mostly batch data because normally we collect small wedges of micro-ED data and to combine those data to be able to determine the structure. And with this real data collection, you get a lot of statistics, and which you know that if the resolution is good enough, if the CC half is good, or the completeness is good. And we can also refine the parameters to make the data, to merge the data based on the clustering through this one. And so this is an example of the MTH1 with this ligand. If you can see here the statistics from Autolay in real-time monitoring, and you can see that, okay, the resolution of different crystals are different, vary a bit. And so you can select the good crystals, and specifically the completeness. So we know that how fast, what is the data completeness, and if we have enough data. So this is important information to see if we are happy with about our data. So this is so the data collection. We collected 18 data sets. So this is the merged, so to look at the CC half to see if they are good enough. So you can see that when you just merge the first 5 data sets, that's you only need 30 minutes, and this is the completeness. And so this is the structure you will obtain. And then if you can work with even longer time, and then you get this structure. So that basically with a few data sets with a half within 30 minutes, you're able to know if you already have the ligand or not in the crystal. And so that this is the structure comparison, zero-ED, micro-ED, and XRD data. And you can see that zero-ED data and X-ray diffraction data, they are quite similar from different ligands. And for micro-ED, because the resolution is much lower, so some of the distances here, they are much longer. So some distances are longer, different than what you get from X-ray diffraction. Yeah. And so this is the structure of another protein called with the dye-type heme peroxidates. So and the 1.3 angstrom resolution, and we want to use this one to show if there is beam damage of our data. So because this protein has been used for studying the beam damage using synchrotron, it's called, and using the distances between iron and the water. So this is the iron and the water distance. So this is, you can see here, for zero electron diffraction, so we obtained 1.3 angstrom, 42,000 crystals, and compared with 0 femtosecond crystallography using XFEL, and the resolution is 1.88 angstrom, 72,000 crystals. And the XFEL data is normally regarded as damage-free. So this is the iron and the water distance, which is here. So 0. This is the femtosecond X-ray X-FEL. Our distance is similar to X-FEL data. And if you look at the micro ED data, and we have the distance here, so that this shows that we have much stereo electron diffraction really has very low radiation damage, similar to X-FEL. And yeah, so this is oh, sorry. And so the next one we want to show is the to see how can we look at the charges, because if you look at use electron diffraction, you can see that this is iron 0, and they have charges. The scattering factors is very different, so that it should be able to determine the charge using electrons. We studied iron enzyme, so that is this is the oxidized ribonucleotide reductase 2A, R2A we call it, and we modeled. This is the structure. We used scattering factor neutral 2+ and 3+, and we find out actually the neutral scattering factor fits the map much better than the iron 3+, because this is the oxidized form. We know that it is. But why? So we want to find out, is it because of the reduction of the beam? Is it because of the scattering factors is wrong? Or it is because our data is not good enough? And all these ones, as we showed, using stereo electron diffraction, we have minimum beam damage. So that we went to look at if there is a better way of modeling the scattering factors. Because the current scattering factor we use, we mainly look at the independent, like atoms. So atoms do not really interact with others. So because this method, it doesn't work really with proteins, so we start with a small molecule. So this is this is the molecule. This is the independent atomic model, as you see here. And we do see a lot of negative densities and positive densities here. This is, we used all atoms neutral, independent atomic model. But in collaboration with Paulina Dominiak's group in University of Warsaw, and we applied this transferable aspheric atom model. It's called the time model. Basically, it's multipolar scattering model. It assumes that atoms in the same chemical environment will have similar atomic scattering factors, but different chemical environment will have different scattering factors. So from this one, we can see that using the time model, and we still keep the iron neutral, actually we get quite good, much improved map. And if we use modeling the iron 3+, and the map really doesn't really improve very much. And so that that means that it is important to model the ligand to the atom, to the metal, in order to get very better fit for the map. So this is how the charge really look like. This is without refinement. So you see that iron is we find out is 1.86, and so the oxygen is about -1.2, and then the carbon it's charged, positively charged, then we go to further, and it's almost 0. So this is the distribution of like charge even for the iron 3+ atoms. And so with this, so we moved to this protein, so R2A. And so we started, this is the oxidized form, this is reduced form. We do see that in this 2 iron, and so this the coordination of the iron changed by the reduction, and so that the water molecules disappeared. This is the zero electron diffraction structure. And so if we compare the structure. We both like the oxidized structure, we reduce the structure, then we reoxidize this structure. So that's the three different structures. As you can see, the molecule, the reoxidized structure is similar to the oxidized structure. So that shows that we really can use electron diffraction to study this very well. So this is the mutant type and this is the wild type. They are all closely related. And interestingly, so that we can look at our structure obtained by CRED and also the structure obtained from the X-ray free electron laser, SFX. And so you see that the structures, both the oxidized form and the reduced form, they are very close. These two structures with the RMSD, as you see here, is 0.26 and 0.21 angstrom. And so this one means that actually we can really study, use steroid to study the structure and get very good, as good as X-FAIR, which is very rare in this one. Yeah. Yeah, so we shown that there is it's important to use multipolar scattering factors to model the ligand. So in cooperation with Paulina Dominiak and also the Phoenix team, and we actually now started to implement the refinement in Phoenix. And so we made this communication. This is the time model, and this is the CCT box. And so with this DSCAMP, and we can call the scattering factors of the using the time model, and go back to use this model for the structure refinement of proteins. And just for your information to show what is the advantage, you can see here, when we use the time model, if you use very high resolution, this is the simulated data. As you can see, using all data, actually the two models do not, this is the electron density, this is electrostatic potential, you don't see very big differences. The important thing is that at the low angle reflection, I showed you the scattering factor, so the low angle differ a lot. It's about below 4 angstrom. So when you use that one, so you can see the electron density actually are very similar. You don't see very much difference, but from the independent model, the time model, you can really see the charge now a little bit. So that this is the difference between these two. You can see the here it's positively charged. This blue, this is negatively charged. This two fit well, it's neutral. So there is a hope that we can use now the refinement in Phoenix to implement using the time model. And this works both for diffraction and also cryo-EM. And so this is my summary. So I have shown to you that we can now get high resolution, high throughput, and low damage CRED workflow. So for micromolecular structure analysis, this is the whole process. So you get the batch screening of your crystal. You use the RAMIC to get the microcrystal micro-sized crystals, and you can use the ligand soaking on grids to generate to study the ligand protein interactions, and you can use the grid square to look at the grid square to collect serial electron diffraction data using the continuous stage movement, and you get a lot of data. Then you can use the data to merge the data integration to finally get the structure. So all these workflows are well developed. So now we can do optimized for protein crystallization, cryo-EM, sample grid preparation, data collection, data processing. And the hardware we are using is very simple. It's all cryo-EM microscope, just with the standard theta D camera, and it's controlled by the serial EM. And so this is the typical frame rate we can collect. And for the studies, biologically relevant structures, protein ligand interactions, aqueous water and hydrogen positions, and also charge state, hopefully in the future. So with this, I hope I convinced you that electron diffraction will be very useful for your study in the protein structures. And with this, I would like to thank my students. So all these people are involved in developing serial electron diffraction, and also the group in Warsaw, and also protein R2A. And we are working with the Scilab lab, where the cryo-EM is located, and the Phoenix developer, and for the protein drug interactions, and all the funding agencies. And finally, thank you for your attention.
Okay, thank you very much, Xiaodong, giving us this really exciting development in your group. I think this is open to questions. Let me see if I could figure out how to read this.
Should I close my screen sharing?
Yeah, right. Yeah, you may. Yes. Okay, so there is not Q&A in this.
Yeah, I've got Q&A here.
I see.
Within the additional, there's a question from Michael Schmidt. What is the dose per crystal in the continuous data collection case?
That's a very good question. Because we are using one frame, so we usually want to get a higher resolution, so we are using higher dose. So basically, the normal dose is about a few electrons per square angstrom per frame, about 3 to 5.
And how many crystals are you averaging for these this sort of resolution? That's my question.
Yeah, so the higher the more the data, and the better the resolution, the better the data quality. We have showed that using a few thousand diffraction patterns would be good enough.
Okay, so, and what is the electron detector you're using as well?
Theta D. Theta D.
What kind of microscope you use?
Cryos.
Titan cryos.
Titan, yeah.
Okay.
Yeah.
So these are all done at low temperature.
Yeah, so this is for proteins. For other samples, we are using our material science, like microscope, using a hybrid detector, where you can get much better resolution and much faster data collection.
Well, I don't know if you can see the Q&A. Next question is...
I cannot see it. I don't know what's wrong with my...
Okay, so do you want me to read it? So
yeah, would you please? Yes.
Yeah, thanks. So what are the, how are the hydrogen positions determined, and what are the uncertainties?
The hydrogen positions are shown, as was said, in the difference Fourier map, and you just pick them up, and we don't really. I think I just showed you that the distances are, if you don't try to refine it, it's about, there are some errors. It's like 0.8 to 1.2, and if you just look at them directly from the density map, of course you can do the refinement. When you do the refinement, usually you probably make some soft restraints
Thank you. And then considering the stronger multiple scattering effects in electron diffraction, could the use of kinematical approximation impact the refinement in the results? And what was the dynamic refinement evaluated? Was it
we did a lot of studies for small molecules. No, because it's not possible to do the dynamical refinement of proteins. We find out dynamical refinement improves the map and improves the atomic displacement parameters, but the atomic positions are already good enough so that there very little improvement of the atomic positions. When we compare the kinematic refinement and dynamical refinement, our value is generally much lower.
And then when collecting with a tilt, how often do you have to readjust the stage height to stay U-centric? And is this automated in your system?
For CRED, you don't need to do any adjustment. And when you actually sweep and stage movement, and we don't do any adjustment. The sample height stays because actually the beam is not moving. It's just if you tilt the beam, and actually the crystal is sliding like this, and the height is always the same.
Okay,
so we do not adjust the height.
So you're tilting the beam as well as the specimen?
No. The beam is stable, and then we just move the grids.
So what you're saying is you're doing a fixed tilt angle. You don't move around the tilt angles.
No. Yeah, we just use the same tilt angle.
Right. So it's a fixed tilt angle, and you move the sample only.
Yeah.
And so you have crystals at different orientations.
That is the whole point, I guess.
Yes. Yeah.
And is there a molecular weight limit to the size of the proteins you can use?
That's a very good question. And we are mostly focusing on relatively small proteins. And this is also complementary with cryo-EM, where it is very good for large molecular weight. And this really depends on how thick we can really study. So if you have more like plate-like crystals, we need to have large enough number of unit cells. Otherwise, there should not be a big limitations.
So what is that molecular weight? You said small and large. So what are they approximately?
Yeah, we have about 100 kilodalton. So this is mostly we have been studied. So
I guess if you have too big a molecular weight, you may get into more dynamical scattering as well if you get a thicker crystals.
we can't really study too big crystals because they're too thick, and then you don't the electrons
right.
will not
Bigger unit cell spacing.
Yeah, exactly. So.
And another interesting question: have you encountered a mixture of crystal isoforms or chiralities?
Yes. So for small molecules, yes. And then we can do what's kind of phase analysis. And for proteins, normally we do not. So basically, you get the same form when you make the crystallization. And for different crystallization conditions, you get different forms. Yes, we do.
I'm wondering, because Colin is our local expert on 4D stem diffraction, if Colin has any questions. Colin?
I guess my only question related to that would be, have you tried using the scanning mode instead? Like I know there's some collaborations, for example, TestScan is looking at serial ED and micro ED to try to sort of merge the two techniques. Have you experimented with that, or is it still the classic diffraction?
We for this previous serial ED, and we are doing the beam scanning. but this one we don't. The thing is that would be a very good idea to try. Yeah, currently we don't have the scanning and from the cryo. Yeah.
You do need both, yes.
Yeah.
And then you could also scan different points in the scan system as well as the going from plate grid to grid as well.
Yeah.
Yeah. So, Wah, I think we're close to time. Do you have any wrap-up questions of yourself?
No, I don't. And I think this is extremely stimulating. I have a few more questions. Maybe after Christoph Koch talk, and then you can stay around, Xiaodong, and we may have some more questions after that.
Right.
Okay.
Okay,
Yeah.
good. All right. Thanks so much. I turn back to you, Bob.
Thank you.
Thank you. Wow, it was brilliant, Xiaodong. Very stimulating and useful for both bio and material science people as well. And so before we go on, I'll ask Prasanna to make sure that we have a copy of the Q&A. There's still a few questions left. And if Xiaodong cannot access it, then maybe Prasanna can make a copy and send it to her so that she can respond appropriately. But meanwhile, then that was fantastic. I'm looking forward to Christoph's talk next and hand it over to Colin to introduce Christoph Koch.
All right, thank you, Bob. It's my great pleasure to introduce Professor Christoph Koch. He originally got his undergraduate degree in Germany. I actually forget where, Heidelberg, but then did a PhD in Arizona under John Spence, the unfortunate late John Spence, very famous in electron microscopy. And in around 2011, I believe, moved to Ulm to become a professor there. And shortly thereafter, in about 2015, moved north up into Berlin. And he's been there ever since at the Humboldt-University, running their TEM data research and structure group there. And he's very well known in our field for pioneering a great number of different methods. My own group bases a lot of our software approaches on early papers from him. And I've had the pleasure to visit his amazing facility several times. So very much looking forward to his talk. And I really hope, too, we're going to get to hear a little bit about the data science side of electron microscopy, because Christoph is also one of the spokespeople for the Fermat Consortium in Germany. Christoph, do you want to share your slides? You're also still muted, too.
Can you hear me now?
Perfect. All right. Thank you very much for accepting our invitation. And we're very much looking forward to your talk about observing atoms in motion with fast electrons. Take it away.
All right. Well, thank you very much, Colin, for this super nice introduction. I have not prepared too much on the data science part, although there's one slide and maybe I will talk a little bit about it. Anyway, yeah. So the title I gave this talk was Observing Atoms in Motion Using Fast Electrons. I will include the people or mention the people that have actually led to this work when it comes to that. But let me first introduce where we're from. So this is Berlin, Germany. You may recognize here at the horizon the TV tower that some of you may have seen on pictures or even in live. But in the southeast of the city, there is the Science Park, which is actually Germany's largest, and in Europe, it's the third largest science park with 1,300 companies and a number of different non-university and university research labs. And the physics department is positioned right in the middle, and that is the building that you also see behind me. There's also synchrotron on site, for example, and many other facilities. So this is the Department of Physics from the top. Next to it, there's the Center for the Science of Materials, Berlin. And a number of these non-university research institutions and ourselves have put electron microscopes into these two buildings. So that actually becomes now a very nice environment for a very wide range of different applications of electron microscopy and, of course, also technique development. I won't go into all of this, but limit myself to imaging the phase that actually electrons experience when they scatter through materials. So when we accelerate electrons, for example, using a 200 kV electron microscope, they have quite a short wavelength, that's like 70% of the speed of light. But when they then see the positive potential in the material, for example, this atom here, the wavelength shortens. And that means when they arrive on the detector, there's a phase difference between parts of the electron wave. So it's always only one electron, even though I put two blue dots here. Parts of the electron wave that have traveled through vacuum or a different part of the sample and this atom here. And this phase shift allows you then to actually know that there is an atom and also recover what the Z number, for example, of this atom is. So when you have a material, what actually happens is that this plane wave, so we assume there's a plane wave coming in, when it actually sees a column of atoms, it bends around. So the phase of this wave function is bent, which leads then to propagation, which is always, of course, normal to this wavefront, that you can compare to the scattering picture here by the potential of the atom. So both actually represent the same thing at the end. Here on the right-hand side is the wave picture, and here is more the scattering particle picture. We now actually work mostly in this wave picture because that helps us to do a number of things and also simplifies the simulation quite a bit. The problem with modern microscopes that have aberration correctors is that you eliminate all the aberrations if you've really tuned them to minimize them. And then you can actually observe only the scattered intensity. And if you have a thin sample, which only has a phase shift like this, then you don't see anything. Actually, this phase shift is lost. And actually, this has led to a number of techniques being developed. Going back to Denis Gabor in 1948, when he invented this principle of holography, pretty soon after with lasers, there was this off-axis scheme developed. And then also when the field emission source for electrons was developed, there was then the Millenstein biprism, which allowed then a reference wave going through vacuum and the reference and the object wave going through the object to be interfered and producing this interference pattern, which you can then interpret, for example, on an optical bench where you can do Fourier transformation and back Fourier transformation, so Fourier filtering, or in the computer nowadays. Then another technique is this inline holography, where you actually use images at different planes of focus, and you then, to overcome the twin image problem, so you can also call this focal series reconstruction. It's also a technique that is widely developed. And another technique is these 4D stem-based techniques, where you can have, for example, differential phase contrast, which can be executed using a detector like this one, so a segmented detector, or actually nowadays with these fast direct detection cameras, there are also other techniques like, for example, center of mass, which is very similar to this DPC technique, or what I will mostly talk about today, this technique of tachography. So the idea is you have a focused probe, or nearly focused, or at least with a small size that you scan across the sample. You might also defocus it if you really want to limit beam damage. For example, in life science, people apply defocused tachography a lot, but also in material science, this may have an advantage when you want to minimize the damage due to dose. And then you scan this beam across the sample and you collect the diffraction pattern at each probe position. And so, yeah, what is the ultimate limit that we can go to? As I've already mentioned, Denis Gabor has overcome or has had the intention of overcoming the spherical aberration limit by developing this spherical aberration technique. Excuse me, overcoming the spherical aberration by inventing the holographic principle. And then first sub-angstrom images were actually also produced by a type of holography. That's this inline holography that I mentioned to you, this focal series reconstruction by Michael Keefe and also Christian Kieselowski and so on were involved. More recently, we have then seen by the group of Dave Muller that tachography has overcome the information limit of the microscope, and then also now reached the limit of thermal vibrations. So if the atoms actually shake, you see them a bit blurred, and this blurring of the atom positions has actually been determined to be the limit, and that is at about 0.25 or 0.3 angstroms. And the question is, can we go further? So can we overcome this barrier of the vibrational frequency of the vibration of the atoms, and can we even use this technique, this phase imaging technique, to visualize the vibrations of these atoms. So my talk will be actually discussing mostly that topic, actually, to really recover these atomic displacements and phonon dispersion using tychography, but also show that tychography really can also overcome the resolution limit of 1 angstrom in a conventional SEM, but also we'll show a little bit about this data science, especially focus on making tychography accessible to everybody, even those people who don't really know how to use these techniques. I'll come to that later. So the instruments that I will use, or that we use for these experiments, this is a neon Hermes microscope that has a monochromator, so it can also have very high energy resolution of about 6 milli-electron volts at 30 kV accelerating voltage. But even at 60 kV, it has a sub 10 milli-eV energy resolution. And it has a dextrose ALI detector, direct detection camera, which is really essential for these experiments because it allows us to detect single electrons. And the spectrometer in this microscope can not only produce yield spectra, but also produce energy filtered or zero loss filtered diffraction patterns. And this is what we're going to use for this tychography work. I will also show you some tychography done on this very simple instrument here. This is a Zeiss SEM that goes up to 30 kV, has no particular electron optics in it, except it has a field emission source and then a time peaks detector for recording diffraction patterns. So using this yields system attached to the neon Hermes microscope, actually Benedict Haas has been able to record maps of phonon spectra across a grain boundary, or actually 3 different grain boundaries in a silicon sample. So this is silicon 110, but there was a triple junction of 3 boundaries. One was a sigma 3 boundary, another one was a symmetric sigma 9 boundary, and another one was an asymmetric sigma 9 grain boundary. And you can see here from these STEM images, they were actually recorded with a high current setting, so we don't have the ultimate resolution in these images. Changing that would actually resolve easily the dumbbells, but recording with these high current settings and the small monochromator settings, these yield spectra, then it was able to actually see yield spectra basically at every position here. And here you can see a map which filters only the 60 milli-eV peak. So this is the basically putting a filter on the spectra, showing only the 60 milli-eV peak. That is the map he got. You can still see the atomic columns, but you can also see there is no contrast going from the left grain to the right grain across this grain boundary. So actually the grain boundary is basically hardly visible. You can see the atomic columns and you can see the structure, but the spectra actually don't change. And these are 3 different spectra, one from the left-hand side, one from the middle, and one from the right-hand side, which actually all look the same, the experimental spectra. And what I've done is I've built an atomic structure that actually has exactly these atom column or these dumbbell positions in it, and also this grain boundary. And we gave it then to the group of Peter Wess and Tara Boland at Arizona State University, and they've been doing some MD calculations and extracted then the phonon density of states, and they were also not able to see any difference. But going to the sigma 9 grain boundary, you can see there are these pockets with 7-membered rings. And actually the phonon spectrum, if you focus on the 60 milli-eV peak, actually does change quite a bit. And if you go to the asymmetric grain boundary, you can see the structure is even more or less symmetric, and you can see even bigger pockets of different structure, and you can see the deviations being even stronger. And you can see the deviations are mostly affecting the 60 milli-eV peak, not so much the 40 milli-eV peak. The red curve is always the boundary, and the gray and the black one are the grain on the left-hand side and the right-hand side. They actually coincide. And you can see in the MD simulations, this reduction in the intensity of the 60 milli-eV peak actually is reproduced. So what we learn from this is the MD calculations actually reproduce what we see in the experiment. And so why don't we just now work with more than just the energies of these phonon modes, but also the eigenmodes of these vibrations? And that is indicated here. You can see there are different eigenmodes which have, of course, different spectral density. This is around the 60 milli-eV peak. They focus, actually quite a few of them in this range here. And you can see now these atomic displacements associated with each of these energies. So we have the atomic displacements in the model, which reproduce the Eels experiment. And now we have something realistic in hand that we can do some simulations with and see if we can also recover the vibrational eigenmodes, not just the energies, but also the correlations between the motion of the atoms. And why do we expect this to actually be visible? Well, there's this paper from 25 years ago by Dave Muller in the group of John Spence at the time, where he showed that if you actually simulate the thermal diffuse scattering using the Einstein model, you get the thermal diffuse scattering, you get these Kikuchi bands, which many of us have seen before, but there is no structure in these Kikuchi bands. But if you actually work with the detailed phonon model, which he was able to actually use because he knew the force constants between the atoms and was able to build this dynamic matrix of silicon and then produce these displacements, you actually see that the thermal diffuse background looks different. It has these bands in here, which don't appear in this Einstein model simulation. And the question is this also then recoverable in thermal diffuse, in tychography? The question, of course, has an answer, and I wouldn't talk about it if the answer wasn't yes, or at least you can make an impression yourself if you look at these slides. So to simulate these thermal diffuse scattering patterns that I showed on the previous slide, what you do is you actually shake the atoms and you produce a diffraction pattern for each displaced configuration of atoms. And if you want to do it right, you also actually move the beam a little bit and convolute the diffraction patterns in real space to account for the effect of partial spatial coherence, because we always have partial spatial coherence in our experimental data. And so you can do this in tychography as well by doing exactly the same thing, only in reverse. So what you do is you, instead of simulating only a single diffraction pattern for each probe position, you actually simulate the diffraction intensity by summing over all the static displacements and all the different probe modes in your beam. So let me show you how we do this. Since this work by Wouter van den Broek, who was a postdoc in my group but now works for Thermo Fisher, we've been using these artificial neural networks to actually represent the scattering of electrons. So you have this incoming wave, which you can treat basically as the incident layer in this neural network. And the object then has these different weights, which are the potential voxels in your 3D potential of your object. And then, of course, you have a weight that comes out at the bottom of your sample, and you then compute the diffraction pattern from that by taking the Fourier transform and squaring the amplitudes. Well, if you actually now want to simulate this thermal diffuse scattering or include the thermal diffuse scattering into your tychographic reconstruction, you need to have multiple objects, not just one, because one would only be able to have one configuration of atoms. And so they might either have a shared input wave, and then you have different objects, and you then basically put the same wave into each of these objects and then have different configurations of potential in here and sum them all up. Or you can also have, of course, a pure object, but different probe modes. This would not simulate the thermal diffuse scattering, but would actually account for the partial spatial coherence, which has been developed in the group in Sheffield on this. Or what we do is actually have now multiple probe modes and multiple objects. So really accounting for both partial spatial coherence independent of the thermal diffuse scattering. And how is the thermal diffuse scattering implemented? Well, we first do a single object reconstruction until we get a decent reconstruction result. And then we make basically copies of this object, 20 copies, for example, and then add a little bit of random noise to each of these copies so that they're not the same. And then they can develop independently. And what comes out is that you have now, this would be a single object reconstruction, where you actually, when you have a diffraction pattern that includes thermal diffuse scattering, where you can see there is this high frequency noise in here, But when you then have multiple objects and you average over them, you can see that you have also information out to higher angles, and also this noise actually at the high angles is reduced. So this is what the average reconstruction. But we can also, of course, keep the individual objects and look at what they look like. So this, because we have a simulated structure, we can actually know how the atoms have moved. And this would be the displacement of the wet dots here. So taking a few of these atoms, given the numbers, and then seeing how they move and plotting their displacements relative to the mean position, this would be the wet dots in the original MD simulation. But then the recovery from the simulated thermal diffuse scattering simulations, from the recovery tychographic reconstruction from these simulated diffraction patterns, then gives us also displaced atoms. You can see here that they're moving slightly, and these displacements are then these blue positions, which you can see they don't have quite the amplitude, and they also are different positions, and that makes sense because we don't expect to recover exactly the same displacements. But as I will show, you will see you will see that the correlations between the atoms are actually quite correct. And just for sanity check, if we don't displace the atoms at all, so we don't put thermal diffuse scattering into these simulations, and we go exactly the same reconstruction route to also recover multiple objects, you can see that the displacements in the reconstruction, they're actually quite small. They're almost negligible, and many of them fall on top of each other. So we really only see these displacements when we have actually thermal diffuse scattering in our diffraction patterns. So what we can do now is we can now give numbers to each atom and number them and plot now. This is now a plot like this, where we plot all the atoms, the atomic numbers in one dimension and also in the other direction, and now see correlations between them. So we have now the displacements in the x direction, the displacement in the y direction correlated with one another. And of course, for x and y, we always see along the diagonal that they're fully correlated. So that's why we expect a line for the x and the y displacements. We also have the xy and yx displacements, which of course are expected to be mirrored. And we only plot the expectation value here, basically averaging over all the different modes that we recover. And this is the original object. This basically are the correlations from the MD simulations. And we can see here, these are the correlations when we do the reconstruction using this multi-object reconstruction with partial spatial coherence included. And you can see here, the amplitude actually is lower than what we expect from the MD model, but the correlations actually are quite well reproduced. And let me show you this also on a different example. So this is now an experimental data set. This is a stack of 2 HBN crystals with a twist between them. This was produced actually by one roughly 9 nanometer HBN crystal, which was folded over so that but the folded over part is now twisted with respect to the underlying crystal. So we have now these 2 crystals on top of each other. And you can see if you do the tychographic reconstruction and you sum all the different slides together, you can see actually there is this more rate pattern. From that, you can determine the twist angle and so on. But this was a 3D reconstruction with 2 angstrom slices. So the slices had 2 angstrom thickness. And if we now plot a line scan through these atoms here, you can see there is an atom at the bottom and at the top. And this is the atom at the top, which then stops in top layer and then it disappears in the bottom layer. But at the same time, because the line scan also went through another atom, there is another atom here. Sorry, these are 2 different line scans. I apologize. 2 different line scans because they always start at the center of an atom. But this is an atom in the bottom slice where you can see really it only appears in the bottom slice and not on the top. And from that, we can roughly determine the Z resolution to be approximately 1 nanometer. But in addition to the 3-dimensional slices, so these are now the 10 slices that have been recovered. This is an older result. It's not the most recent one. So the Z resolution has actually become a bit better. But what I wanted to show you and what's most important to me here is in these slices, this is a top slice where you can see that the lattice is inclined a bit relative to the horizontal. And in the bottom slices, the lattice is actually aligned horizontally. But you can see that also the atoms are moving, right? You can now see really there is some displacement between the different objects that we've recovered. And these displacements are now being analyzed. But before I come to that, let me also show you the diffraction pattern that Anton, that's basically the PhD student who has performed this work, has now carried out on these 3D reconstructed potential slices. Because we have the potential slices, we can now also run any other multi-slice simulation through it. So now producing a multi-slice simulation with a convergence angle of only 3 milliradians, so that the disks, these seabed disks, don't overlap. You can now really see also the diffraction pattern. You can see again this twist angle. But what you can also see, you can see the higher order Laue zone. Right, this corresponds exactly to the first order Laue zone of HBN, which has a C lattice constant of 6.6 angstroms, and then at 60 kV, which was the voltage that this experiment was carried out on, you have these 2.3 inverse angstrom spacing, which is outside the detected range. So interestingly, multi-slice reconstructions actually allow you to recover diffraction information, which is outside your detector range. And because these high scattering angles were not even recorded in the diffraction pattern. And then from these data, this is now the top slice. This is this is now the lattice from the top half of the crystal. This is the lattice from the bottom half of the crystal. We can now extract correlations, and these correlations between atoms we can then put into the dynamic matrix, and then invert this or find the eigenvalues and eigenvectors of it, and extract from that then the dispersion curve. So this is the same that I showed you this image by David Muller, which he has put into these MD calculations, which then produced this STEM image with the thermal diffuse scattering. And now this goes the other way around, taking basically this diffraction pattern information and extracting now the dynamic matrix, and from that also the eigenmodes and eigenvalues. And they correspond almost to the ones that we expect for HBN, hexagonal boron nitride, but they're a bit lower. And the reason for that is that we don't have full Z resolution yet. We only have about 1 nanometer resolution along the Z direction. And that actually reduces the amplitudes of the displacements, but the directions of the displacements, we've checked this, actually are preserved. So of course, one can combine this now with heating experiments where you change the temperature and then see basically how higher order modes are also excited, or more strongly excited. So we recently done some laser experiments in this same microscope where we now shine a laser onto our sample and produce then maps of the local temperature. And this can be done by the principle of detailed balance. There have been papers by Marine Lagos and Phil Batson, but also from Carlos Hidrobo, on really using this energy gain and the energy loss peak in yields spectra of these phonon modes to actually determine the temperature without any reference. And so in this graphite sample here, they were able to actually heat it up to 2000 degrees and more, and actually convert also amorphous carbon to graphite and so on. But there's an archive paper that you may be able to find out more on this. Let me just finish by 2 very quick topics. So one of them is this tychography technique, because it doesn't require necessarily any post-specimen optics, can of course also be carried out in SEM. So here's some early work by Xiaodong Zou, and she reanalyzed data that was recorded in the Sheffield group, and really was able to produce a 2.3 angstrom resolution reconstruction of these gold nanoparticles on amorphous carbon. More recently, actually very recently, there's this publication by the group of Arthur Blackburn, who showed really sub-angstrom resolution down to 0.67 angstrom resolution in this microscope, which has a twin pole piece. So it's called an SEM, but I would want to call it a low voltage TEM. But it also uses TEM holders actually to load the sample in there. But at 20 kV, this is quite an improvement in resolution beyond what the microscope can actually do. And now this simple SEM that I've shown you, the microscope that we have in our lab, where we put a time pix detector in. Unfortunately, we didn't record the information out to very high scattering angles, and have not really used multi-slice tychography yet, but even this is the range of the detected scattering angles, and really the resolution goes all the way out to where we've recorded information. So we should repeat the experiment now. This is a very recent experiment, but we should repeat it now really with larger scattering angles and see how far the resolution can go. Interestingly, in contrast to this microscope I showed on the previous slide, which had a cold field emission source, this has a regular field emission source. And so the virtual source size was 3.4 angstroms, yet the resolution we extracted was less than 1 angstrom, actually. Yeah. And because, and I finished almost, this is my last slide now, just this little movie, this data management research infrastructure that Colin mentioned initially. It's actually this Nomad platform, and this is an open source software which you can download. Actually has also tools to run software online. So you can run your software directly online where your data is. And this is now demonstrating the use of a chatbot, which runs in this Neon Swift software, which is also open source. That's why we were able to actually put it there. You open this chatbot and can talk to it, and you can tell it to do a tychographic reconstruction. And then we'll find out together with you what the parameters should be and fill out basically this graphical user interface where these parameters should go. And once you've figured out all the necessary parameters and it's happy with the information you gave it, you can then start to actually do a reconstruction, which is then pushed off to our GPU cluster. And while it's waiting for the result, you can also ask it, well, do a DP-seq reconstruction or do something else. In this case, since we already have a 40-stem data set, we asked it to do a DP-C reconstruction. And after asking what the convergence angle and the rotation angle between diffraction patterns and the scan is, it will actually produce this IDPC reconstruction for you. And since we've now waited, this whole movie runs actually 4 minutes. I sped it up to 2 minutes, so this is a factor of 2. It will also give you a tychographic reconstruction, or at least an intermediate result. And then it will also show you the convergence curve if you ask for it. Right. Anyway, I think my time is up, and I don't want to go into overtime, and finish with this last slide where I summarize and was hopefully able to show you that holographic techniques really have always been at the forefront of the resolution in TEM. I mean, this is what they were invented for by Dennis Gabor. And now I consider basically tychography also a inline holographic type experiment. You may debate this, but I think it has there's some justification for this. And with this inline holographic tychographic technique, you can now even overcome the resolution limit of microscopes and also even show how the atoms vibrate, or at least get closer to this. And if you combine that with yields where you can get only the energies and maybe the dispersion for high energy losses, in phonon losses, you can now even recover also, for example, the acoustic modes. Yeah. And with that, I thank you very much for your attention.
Thank you, Christoph, for a very amazing talk there. So I will quickly remind the audience that please, if you have questions, paste them into the Q&A, and then we will ask Christoph for you here. So Christoph, first question from the audience. Natash Balsara over at Berkeley is asking, can you study crystals where a species in the lattice exhibits translation, not just vibrations?
Well, okay, so let me just stop this so that I can see you better. Where the atoms
yeah, he's asking about translation, not just vibration. So I'm not 100% sure what he means, but maybe like translating very far in one direction compared to the other, like you know, different phonon modes, for example, in different directions or amplitudes.
Well, I think you should be able to, right? If they're displaced by a large amount, and so what we actually recover is these atomic motion during one frame of the acquisition. So as I mentioned before, I hope we don't have the sequence of how these different snapshots actually occur, but what we recover is we recover the motion of atoms that cause this incoherent scattering in our diffraction patterns. And if during one frame of the acquisition, the atoms shift, this should also be recoverable if they shift relative to the others within the field of view, right? So it's always relative displacements. In diffraction, of course, we don't measure absolute shifts, right?
Yeah. Okay, so George Farnabides at TU Delft is saying, in the Blackburn paper, in addition to the cold fag and the twin pole piece, the other hardware element that they added was that custom projector lens. So in your Zeiss SEM, how do you get around the limited camera length, and what convergence angles can you achieve?
Convergence angles are quite small. I think this data that we've done the reconstruction with was recorded with, if I remember correctly, 6 milliradians convergence angle. And the large camera length, well, we got by really putting the camera, this time-fixed camera, at the bottom of the microscope. Right, so we actually shifted the stage to the side a bit and placed the camera at the bottom, so that we had as large a camera length as possible. But now that we see that we really need to have the high angle scattering to get even higher resolution, I'm wondering whether it actually would make sense to move the camera up a bit, to reduce the camera length a bit, so to collect also the high angle scattering.
Yeah,
there's different ways that we're trying to do this now, but these are very recent results, so we don't really have much experience with this yet.
Yeah, we need projector lenses in our SEMs. Should be added. Okay, so Nestor is asking,
Colin, I don't subscribe to that statement all the way, because I really think one can live without, and it really reduces the complexity of the experiment if you don't also need to worry about distortions and so on of your projector lens, right? Yeah,
you're not wrong. I just think we can solve those distortions computationally if we're doing picography anyways. So Nestor wants to know, what temporal resolution can you reach?
Temporal resolution. Well, okay. So this that's a very good question. I suppose we don't have really temporal resolution, because basically the temporal resolution, if you want, that we have is the frame basically the frames per second, and the Eller detector actually records 2,200 frames per second if you go on 16-bit mode, and if you don't reduce the sub-range of the detector, it can of course go up to 18,000 frames if you really reduce the bit depth and so on. But yeah, so that's nothing compared to the terahertz frequencies that we look at when we look at these phonons. So we really expect the sample to be the same for every probe position, or basically have undergone the same statistical displacements for every probe position. So I'm afraid there's no real time resolution in this.
Well, so actually, I'm going to combine. Maria Chan over at Argonne has a comment that she thought Natasha was referring to ion transport, and Wolfgang Jaeger says, could you use the technique to study the diffusion processes? So I guess to combine that question, if you had different, say, unit cells or snapshots or whatever, as you're recording the beam, and the ion was moving, from one position to the other, do you think this mixed object state could recover those snapshots, for example?
Ooh, that's another interesting question. I think I think we should really tackle this problem all the way, because we see this not only in diffusion, but our samples are beam damaged. So we see a change in the sample between probe positions anyway. We might actually, and this might indeed be true. So of course, diffusion, we have not only one atom, but you have multiple atoms. So we might actually, if they occur within one frame, that's actually very fast. See this? It's a difficult question to answer, because I would expect the diffusion to be much more slowly than one frame.
Yeah, I was thinking of like oscillations where it's going between two or more configurations. I wonder, what the limit is. But if I had a suggestion, it would be do it in simulation first and see if you could recover a trajectory, right?
I think one interesting case where this should be applied is, these two-level systems that cause decoherence at qubits, where people don't really know what actually is the atomic structure, or what is the atomic origin for these two-level systems. And if they're really atomic structure, you might actually be able to see it this way, right? Because you would see that there's this superposition of two different states, which you might then recover using this technique.
Yeah, that's a really great idea. Kate, did you have a question?
Yeah, I had a question kind of on that, but slightly differently. So your Z resolution is, I guess you said 1 nanometer.
Yeah.
And then you have these atoms, which is more than one layer of the HBN, I suppose. Do you think that the atoms, all the atoms within that layer are within that Z section are moving in the same, are you seeing a superposition of?
Yeah. So, okay. That's a very interesting question. So, and maybe I should actually rephrase my statement about this 1 nanometer, approximately 1 nanometer resolution, because I believe we have along the Z direction these 6 angstrom resolution, because we can see if we actually take these, reconstructed potential slices at this 2 angstrom spacing, and then propagate an electron beam through it, we see the high order lower zone ring at the first order lower zone, which should actually reflect this 6.6 angstrom lattice spacing along the Z direction. So I would say we are able to see 1 unit cell in this HBN. And even if you believe that data, even a little bit beyond that. But indeed, yes, we have this limited, we still don't see the individual layer because there are these, at least you should really have very thin layers to account for the displacements of all the atoms. And we actually found that you have to really do very fine simulation slices in the forward simulation when you want to record or properly account for the displacements in the silicon structure. So there we really used 0.5 angstrom slices to actually get the correct answer. And it turned out, and I do have actually a slice on this. I think this may actually make sense to show again. Just one last slide.
Yeah, while you're pulling it up, I would love to see if I saw 2 Laue rings, maybe I would become a believer.
But okay, this one is from this paper, this archive paper in the supplementary material. It turns out if you actually use slice thicknesses of 2 angstroms and less, you stay below this this error metric. This is like the Gaussian log likelihood that Anton used for this tychographic reconstruction. If you make your slices thicker than 2 angstroms, so this is 2.5 angstroms, then actually the error starts going up. So only when you use 2 angstrom slices, you actually get this good agreement between experiment and simulation. If you use thicker slices, so this is not even 1 angstrom, not 1 nanometer. So 1 nanometer is basically out here to the right. But you have to use very thin slices to actually get this good agreement.
Do you have the same plot with number of object states?
Same number of object states, I believe.
No, like
varying. 20.
No, varying the object states and seeing what the log likelihood is, for example.
Oh, so the same plot for number of object states. I don't have that, but I know that Anton has tried. So this reconstruction that I showed you was with 20 objects, and he's tried also with 30, and it converged. So it didn't show any different result. And maybe to answer, to finally answer Kate's question.
Yeah, go ahead.
Sorry, now I missed you. Let me first answer Kate's question, and you can ask again. I apologize. Kate, you were asking, because we only have a limited Z resolution, do the atoms actually move in sync? Well, that is exactly the reason for why we don't get the full amplitude of the displacement, I think, because they do move differently. So we don't expect the atoms actually to move in sync throughout 1 unit cell. But this might actually be it, right? Because maybe we see only acoustic modes, acoustic components along the Z direction where that are long wavelength, and we don't see the high frequency ones. These are all questions, I guess, that should still be answered. But we see that I think the limited Z resolution causes our displacement amplitudes to be smaller than we should get. But the direction is the right one.
High frequency ones would be smearing, I think, along the beam direction. Okay, Bob, do you have a question, or do you want to wrap it? Or?
Thank you. Yeah. Well, thanks, Christoph. Brilliant stuff, of course. And I'm interested more in combining a few of the questions, which is atomic displacements and time resolution. Hamish Fraser has shown some beautiful results of the omega phase transformation in titanium alloys and shown the atomic displacements there. And we're interested in some martensitic phase transformations, which are temperature dependent in nitinol, which is shaped memory alloy. And so it strikes me that if you were to change the temperature and take the tachographs under ideal conditions during cooling, one might be able to then extract the atomic displacement associated with the cubic to monoclinic phase transformation in a rather important alloy. Do you think that would be possible?
But they only occur once, right? It's not a periodic process that runs at terahertz frequency or at least very high frequency. Am I correct?
So it's a permanent displacement when the phase transformation is complete, but no one knows what happens going from one to the other.
Okay. Yeah, you would have to acquire the whole tychographic data set, which is a sequential acquisition in that very moment when the phase transition happens. I'm not sure. I would first try really probably what Hamish has done already, get very high resolution maps just before and just after and try to map the displacements. The thing is, here we really need something that basically wobbles all the time. And that is consistent basically throughout the 10-second or whatever acquisition time of our 40 system map. Yeah.
Well, I suspect that the atoms are not just permanent displacing at one particular temperature, but are probably moving backwards and forwards. We don't know how rapidly during this transition.
Okay, if they do, then that might actually be a case. Yes.
It's worthwhile doing these very, very careful experiments. Thank you.
Yeah, very interesting. I think we're all super interested in this technique. So I think we are at the end of time, though, and it's time to wrap up our EM-X symposium here. So I do really want to thank both speakers, Xiaodong and Christoph, for donating their time for excellent talks here. And I think there's a couple more questions for both speakers in the chat, but if Prasanna has captured them, we'll try to forward them on after the talk here. Bob, anything else you want to say?
Well, let's see. Yeah, I think Colin has summed it up perfectly. Let me just ask War if he has any final comments, and then I will wrap it up.
No, I don't have any. I think this has been two amazing lectures this morning that stimulate both the bio and non-bio audience. I thank both Xiaodong and Christoph for such an amazing talk. Thank you very much.
Right, and the lessons which we learn from one to the other as well. Multi-crystals and tychography for bio. So we're looking forward to that. So thanks again, and we will stay online for a little bit longer and chit-chat for a while. And but once I finish these remarks, we can finish the recording, and then just people would like to listen to our informal discussion for a few minutes. But like I said, please put in your abstracts for the IMC at the beginning of September this year. And I hope to see as many people as possible in the town where I was born, Liverpool. Thanks very much.
Thank you.
Prasanna, can you stop?